All right. I know it's running. Okay. So what we are going to do is, did I throw up a sample one on the whiteboard yesterday? Okay. So what I'm going to do is I'm going to generate a problem. I'm going to assign a problem, so to speak. You guys just need to watch this. And if you go, I can do that. You don't have to do this actual problem. We are going to look at how would you graphically add these two vectors together. Now, did I write any words in quotation on the whiteboard yesterday? Tip to tail. So the key phrase that you need to remember is when someone goes, how do you graphically add vectors together? You throw that thing out, they'll probably go, okay. You know, whether you really know what that means is a secondary issue, but this is how you add them together. Now I'm going to show you how they present this in a math book, which I hate because it's not the way that you really add them together. If you were given this problem in a math book, what you would be shown is you'd be given some coordinate axes and they would show you F and C actually drawn. So F, and I'm going to do these in different colors. I'm going to use black for the first one though. So this one was F, and then C would look like this. So you're supposed to add these two together. I'm not sure exactly why they bother to go ahead and start it this way, other than maybe to say, okay, well, these are how the two vectors look on your base coordinate axes. But you can't leave them like this to add them together because they are not connected tip to tail. Here they are connected tail to tail. This means you have to move one of these around. Now, most people, because this is written as F plus C, would say, well, I'll leave F where it is because it's the first one, and so I need to move C around. And when we first talked about drawing vectors, I think in most of the classes, I highlighted that you can move a vector anywhere around on your workspace as long as you don't change the direction it points or the length, that you draw it. So I can move it theoretically here. What we're talking about is I need to move C so that the tail of C is on the tip of F. Now, if you had old-fashioned like drafting equipment on a drafting table, you would have equipment where if you were to line up your straight edge on this, you could lock your tool in place so you could start to move this thing around, but it would never be allowed to do this, so that you could literally say, I just need to shift this up to here, and then you could redraw it. You guys don't have those tools, so what you're going to have to use is your protractor. And this is where the fact that you have graph paper is going to be helpful to you. And I'll talk about that when we discuss how you're going to add these things together. I'm kind of treating this problem as a theoretical treatment, like how do you add vectors together? Then we'll get into a nuts and bolts discussion about how can you draw it so it's quicker. Question, Manny?
So, could you just move the C behind, so the tape is touching the
Again, you could. So, and this is a good point. If we were to say, how many different ways could you move things around so you could have these two things connected tip to tail? I think you could literally do like 4 different ways. And if we have a moment, I might play around with that and say, you could have done it all these different ways. You still end up with the same answer. Yeah,
So it doesn't matter if we start from the origin.
Well, the very first one, the way that I'm going to present how you should go ahead and do this, you would start from the origin, but this is the part where I'm highlighting how they do this in a math book, and I will tell you why I don't want you to do it this way when you actually go to do this. Because I'm looking, if I was going to draw F first and then draw C, one of my critiques would be, why the hell do you want me to draw C right there? Because it's not in the right place to begin with. So what I am going to do is take you through a couple steps, and hopefully after you see the official way that they show this in a math book, when I tell you, here's the quick way to do it, you'll go, oh, that is so much easier than this. Because you should never have to draw any of the vectors that you're going to add together more than once. But when they say, draw this for me, now add them together, they are forcing you to draw the same vector multiple times, which I think is a waste of time. So, but this is how they treat this in math. So what they would have you do in math is, all right, at least the way I drew this, this is about 7.5 inches long. So I would need to make this thing so it's basically parallel. I think I'm all right there. And I'm going to do this with a dashed line to show you that this is the moved one. Now I have my two vectors connected tip to tail. Now if we would have moved this the other way, like Manny was suggesting this, what if we just took this and we moved it like this? This would be C down here. And once we move these things around, we would basically ignore our original one. All right. Now, hopefully in doing this, I'm not overloading people, because you're gonna see way more things on here than you will actually have to do. If I had a third vector on here, there'd be a third vector drawn here coming out of the origin, and we'd have to move it around so it would be, its tail would be on the tip of this C. So the way this is presented in math books, I find to be way too tedious, because they start with draw all your vectors coming out from the middle, then move them around, and there is a quicker way to do this. But I'm gonna try and keep this at least originally so it matches with a math textbook. So once you have connected all of your vectors tip to tail, you are set for your answer. Does anybody know the name? I call it I refer to it as the answer vector, but it has a specific name. The resultant. So in regular mathematics, when someone says, add these four numbers together, what do you call the answer? The sum. When you're doing that with vectors, the answer is referred to as the resultant vector. And as a result of that, when you put any answer, at least from generic vector perspective, when you express an answer, that's what you call it. And it's referred to as the resultant vector. Now, to draw the resultant vector, this is the rule you have to remember. And because we're only doing a two-vector example, be sure you understand this correctly, because this is way oversimplified. If you're doing multiple vectors, when you are ready to establish your resultant vector, you have all of your vectors put together in kind of a chain. To create your answer vector, you take a line and you connect the tail of your first vector to the tip of your last vector. So in this case, it would be that blue line. Now, I'm gonna show you kind of the alternate, because remember we said we set this up two different ways. This was the original way I set it up. But then Manny brought up, well, what if we moved this C over here? If we did that here, the tail of our beginning vector is C, and the end of the chain is F. So if we follow the rule for drawing the vector, what do you notice about the two blue lines? They're parallel. So that means they point in the same direction. Even though they are physically in two different places on our workspace, they point in the same direction. And let's see how we did. This one, at least in my picture, is about 8 inches. 8 inches. So basically those two blue lines are exactly the same thing. So it didn't matter which way I bothered to put, hook the vectors together. As long as I drew them and moved them correctly, I would have the right answer. Now, as far as the answer vector goes, remember vectors are expressed in terms of two, an ordered pair. The first thing is just the letter without the arrow. Who remembers what that represents? Give me the word, the vector word that the length represents. The magnitude. What was the other thing we needed? The orientation, which was covered by, make sure I spell it right first. By what thing?
Theta?
Our symbol of theta. So, getting the magnitude for your vectors is going to be super easy, because at least for these graphical vectors that we're going to, introduce you to vectors with, the only thing that the magnitude represents is the literal length of the line. So you could just take a ruler and measure it. The orientation, what do you have to put on, and I'm going with this first one over here. What do I got to put on the blue line so that I can determine its orientation? The arrow indicator. So now you got to decide, which way does it point? You got two options. It points this way or it points that way. And this is where I want to say, once you play around with vectors enough, I hope you'll go, why the hell would anybody point it the wrong way? It's like, there are reasons why. All right, so for somebody who goes, I know, or I think I know which way it points, who wants to?
Away from the tip.
What?
Away from the tip it's connected to.
So which way,
So
are you thinking it points this way or this way?
That way. That way.
No. This is the one arrow in your entire picture that will not be tip to tail. And this is where somehow you have to arrive at an understanding so that you can point the resultant in the right direction. The correct answer here is that. Now when you go to draw this, I want you labeling your pictures, so that one will get the R notation. Yeah.
Is there a situation where we're with them?
There are some specialty in situations, but at least for this introductory work that we're doing, no. Yeah, and even then I'm like, it's like a total exception thing. So if anybody ever gives you an option, which way does it point? Always go with this one. Okay, so with this other version that was referenced, the same thing would happen, because here our vector chain actually starts with vector C because of the way we moved it. So our chain starts here and then it goes out to here. So that means our blue arrow would point that way. Okay? Now, we need an angle. If I ask somebody to come up and put the angle in the picture, all right, let's see, Anthony. I want you to just give me the arrow, kind of the angular, kind of thing, and label it with theta where you think it belongs in the picture. Be careful, you're on camera, man. This is pressure.
So because it's the sum of the vectors, I think it should be this.
No.
Oh, no.
What would be your second option? It's not going to be that one.
I don't remember.
You're not sure? Okay, let's see. Do you think you know, Nadia?
Maybe.
All right, let's see.
Is it this one?
No.
No?
Okay. Are you coming up? All right.
Yeah.
Bingo. Now, this is our theta. Does anybody recognize kind of what we went back to measure the theta?
The first one.
We went back to our original set of coordinate axes here. Because remember, this was 0, this was 90, this was 180, this one was 270. Okay, now this one's kind of a trick question. And it's only up here because Manny's suggesting this alternate. And I'm just so that you everybody's so happy about this. The way we process this problem, basically we ignore this. We just did it this way and we're done. If we did it Manny's way, we would be ignoring this, and that's all we'd be looking at. Can somebody come draw me the angle for the answer on that picture? Okay, all right, Manny. And I guess I can give you one hint. You're going to have to kind of add something to the picture. Or at least I would, when I give you the final answer, I'm going to be adding something to that picture to clarify this. So let's see.
Another axis here, and then again this.
You're super close. You added the one, add the other axis. Because how do you know where to start
Here
this?
we go. Yep, there we go. And then from here.
Oh, okay. I'm gonna clean it up a little
Okay.
bit, but I think you got the right idea here. I'm gonna be a little more meticulous. If I did it this way, the beginning of my chain is not on my original set of coordinate axes. But my answer is the same length and it points in the same direction. But in order to measure the angle properly, I need to measure at the tail of my resultant. And so essentially what I had to do was establish a new set of coordinate axes on the tail of my resultant and then measure that angle. So these lengths are the same, they point in the same direction, and these two angles would be exactly the same. Now, when you go to do this graphically, what is the part about all of this that makes it so challenging? Like if you drew it the way that Manny suggested, what would you have to be sure of when you drew these things here to get the right angular measure?
I mean, you'd have to have the angles.
You would have to have this thing perfectly parallel to this thing. And you would have to have this vertical one perfectly parallel to this one. Why is that? What about what you're going to be doing, or let's say what you're using, is going to help you to make sure that you can make that happen? The graph paper. Because all the blue lines, vertical blue lines, are parallel to each other. All the horizontal blue lines are parallel to each other. So when you go to set your protractor up, you can make sure that your protractor stays oriented exactly the way it needs to, because as long as the 90-degree line is parallel to all the vertical lines, you're good there. And you have a horizontal line that, as long as it's parallel to all the horizontal blue lines, that means this is in the exact same orientation it was when you started the problem off. Yes, Jack?
Instead of like measuring it off the paper and having like the possibility of error, couldn't you just find it mathematically?
You could, but I'm challenging you graphically.
Okay.
So that's where we're going to go next. So there are people that once they do this, this is where I don't know if you run into people who are old-fashioned versus, I'll call it high-tech. And I'm going to say, I'm going to point out one thing that kind of goes back to our last unit on forces. For all the people who ran to, oh, mu is just a over lowercase g. That doesn't show me, really, in my opinion, that you know the material. For me, all that shows is that you know an equation. And in order to see, all right, I want to see if you really understand how this fits into the big picture, that's where we go to show me your free body diagram, show me all the arrows, and if you start to balk there and go, well, I got this equation, why do I have to do that? I will tell you, as you go to higher levels of physics, they'll say, that doesn't work. We need people who actually understand the conceptual background of what generates, the quickie equation things. So that's kind of what a lot of this vector stuff is about. The mathematical stuff that we're going to do, the reason we can do it is kind of embedded in the picture of what we're doing. But the beauty is, as you point out, this, to get the right answer, is dependent upon you drawing things the right way. Mathematically speaking, it's dependent upon you understanding how to do the math. But the truth is, they are both connected to each other. It's a beautiful overlap of, like, here's the picture concept and here's the math that goes with it. How many of you have already done, I almost want to say that this is like cheating, at least from my perspective on this, how many of you have actually added vectors together on your calculator? You have to enter it in kind of a special way. Oh, no. Now, here's the thing. That's the math thing. I'll just use the law of cosines. What if I'm going to give you 3 or 4 vectors? Yeah. People who know how to do vectors will say, that's a stupid way to do it. I'm gonna teach you the quick way to do the, like, however many as you need. And that's where I don't think they teach that in math classes. But I don't think the whole idea of adding these things together with the law of cosines, I'm not sure they really even show that in physics, because they're going to say, we have to deal with so many vectors potentially in a given situation. That would take me forever to do that. So there is a regimented mathematical way to do this that is super cool. And it doesn't involve anything past basic trigonometry. And that's where we're going to go when we're done with all this. So I will bait you people who really get into your calculator. Most of your calculators actually can add vectors. You know how I told you what's F? For those people watching this in video, this is like live. This is what really happens in my class. Someone asks a question and I go off on tangents, because I'm off on a tangent right now. This is what F is. and C is so if I said add these two together, you can't just add those two numbers together and say, oh, well, I'll just add the lengths and I'll have the degrees, I'm good. Doesn't work that way. But you can access your calculator to actually just enter these two things on it and say plus, and it will give you the answer. But I am not going to tell you how to do that. If you want to know how to do that, you're going to have to look through your manual, okay, and go to the vector section. But there is, and this is one of the other reasons why, when it comes to test day, I don't let you use your graphing calculators, because most graphing calculators, if you know how to work with them, you could knock this crap out super quickly. But my point is that the people who developed your calculator know exactly what we're going to go through here, so they wrote a program based on it so that when you enter stuff like this, your calculator goes like that and goes through the entire process of what you're going to be doing mathematically, and I'm going to make you knock it out the hard way, so that one day when you do it quickly, you'll be like, I know exactly what's going on behind the scenes here. I just don't have to do all the work. It's doing it for me. Okay, so back to your task at hand now. Once you draw your picture that gives you the answer, your final steps are you have to measure the length, and that would be your magnitude, and then you have to measure an angle, and that is your direction. Now, in this case, you're in the second quadrant, so your angle is going to be between 90 and 180. If your answer, for some reason, ends up pointing, in the third or fourth quadrant, remember the one thing I am restricting you to when it comes to your angular measure is 0 to 360 degrees. So, no negative degrees going down through here. You gotta, you may measure it that way, but you gotta convert it into a positive number of degrees measured around from 0. So this is the idea of what you're doing with vectors when you add them together. You're connecting them tip to tail, and you connect as many as you're being told to connect, and when you're done, you have this chain of arrows, and you connect the beginning to the end, and that's the way it points. So you measure how long it is and an angle based on the tail of the first vector, and you're done. Now, one thing about your drawings, when you go to make your drawings, if the vectors like double back on each other or like cross each other, that is perfectly okay. So if you're drawing all these arrows and you go this way, and then the next one takes you like down here, it's okay for the chain to cross itself. Because in the end, the only thing you're worried about is where is the point that this started at, and where is the point at the end of the last arrow, and those two things get connected in a straight line, and then you do your measuring. Now, I am not going to have you do this, present this, the way that a textbook does. So, I am going to show you the easy way to do this. You got to do F plus C. You start with your first vector. You have to draw a set of coordinate axes. These are like your home coordinate axes. And on your paper, on the back side, because this is where you're going to do these problems, you need to think of your paper divided like this, and treat this area, this first quadrant up here, as like the area you're going to work in. Because I'm going to give you 3 different problems, and the one thing that I've had some people do, and it kind of makes sense, is they draw this at the middle of the paper, and then they do all 3 problems right here, and it just looks like a god-awful mess with arrows all over the place and overlapping because they think, oh, well, this is my coordinate axes. You need to pretend that each one of these sections is like a brand new workspace. And again, if I said, draw me your coordinate axes, people will immediately go here and say, oh, I'll start right there. That is not a good move. And I'll come back to that in just a minute. I'm going to add F and C together. I know that F looks like that, and C is going to go off this way, so if I draw it correctly, it's going to kind of look like that. So, if I want to make sure that this fits on the paper, where should I move it?
Just so it's the top.
Because this is going to be where my original coordinate axis is. So where could I move this to make sure that I have plenty of space?
Down.
I would end up saying, I already have an idea that this is going to just basically stay in the top two quadrants, so I'm going to start my original set of coordinate axes a little bit lower. That way, because one of the worst feelings when you go through and do this is when you go to draw the next vector and you go off the paper. Because I will tell you that there is no reason for you to go off the paper unless you chose a poor starting point. So once you establish your coordinate axes here, you meticulously draw F. Now, what I want you to do, and I am going to ask you to do this on your paper, you need to pretend on the end of F that you have a new set of coordinate axes. So after you draw F, I want you to draw a small little set of coordinate axes there. Then what you are going to do is you're going to take your protractor that you originally had right here, because that's the way you needed to orient it. And what you need to do now is, if I can get this to suck off the, God damn it. You need to move it here and put the center of it exactly on the tip of the last vector, and you need to make sure that your horizontal line is parallel to the blue lines. Doesn't have to be on a blue line, it just has to be parallel to them. And the vertical 90-degree line is parallel to the vertical lines. And then measure your angle for C, which I think is around there. And then take your ruler, draw C exactly where it needs to be and label it. And at this point, you would be done. And then you would take your ruler, draw your R, then you would measure the length of R with your ruler, and then I want you to highlight where the theta is in your picture that you're measuring. And then down here, or somewhere around there, you will have R equals so many centimeters at so many degrees. And then you are done with that problem. Then you'll have a second problem that you'll do in this area, which is not, and I'll go ahead and tell you, your first problem will be a 2-vector addition problem, so it'll be like this. Your second problem will be a 3-vector addition problem, and your third one will be a 5-vector addition problem. So basically the process that you go through for each of the problems is exactly the same. The difference is you just have more vectors to connect together. Anybody have any questions on this? Yeah.
Is there a result line when you have 3 vectors or anything other than 2?
What?
Do you still have the resultant line if you have 3 vectors?
Yes. So the idea is you would have 3 I'm just going to make up random, because I'll pretend that I'm using blue for my resultant vector. If I gave you a problem where you had one that went here, and then a second one that went here, and then a third one that went there, you still have a resultant, and it's from the tail of the first one out to the tip of the last one. So you will always have one of those. All right. Any other questions? This is probably going to spill over to Monday, okay? Because you only get to work on this here. So here are your problems. Let's see, what's our time that we have left? We might be able to knock one of these out. Let's see. I want to. That's your first problem. Your second problem is that one. And let's see, your third one is that's your third one. Okay? And I'm going to ask two things. Well, actually, one basic thing. Add them in the order that they are given here. Because if you do that, the first one, it'll be easy to plan, like where should you start so you can make sure it fits. The second one, you can start a little bit shifted over this way. And the third one, you could maybe start a little bit higher than center, and that way they will be guaranteed to fit. Now, you do not need to introduce these lines officially onto your paper. And this is the part where if you understand this idea that if you have a concept of which way your chain takes you, you could shift your beginning spot, accordingly. You could fit like 5 or 6 different of these types of problems on this single sheet. But the part that sometimes people get confused a little bit with that is this idea that you have this home base of coordinates. You have to have multiple ones at different places on your paper because you're doing multiple problems. Okay, so take the last few minutes here. The beautiful thing here is if you get started and say, I only got the first vector drawn. You got it drawn, you can just immediately come back to it on Monday and draw the next one and keep going with the chain. Yes?
Do you get cold in the morning when you get up and go to the car? Do you get cold?
I'm a little chilly, but I'm okay.